Okay, welcome to the lecture here. We'll get started here in just a sec. We're continuing on with electrochemistry. All right, so we been talking about electrochemistry here, and we started out talking about sort of really basic redox sort of reactions, balancing redox reactions, oxidation, reduction. Again, oxidation meaning obviously for most of the time for our consideration that something has lost electrons becoming more positive, while something that gets reduced has typically gained electrons becoming more negative. And we can really follow what's happening with everybody by following really their oxidation states or oxidation numbers. Again, as we saw, you could use sort of just a basic number line. And if you see that the charge or the oxidation state is getting more positive, then it's going through oxidation. If the oxidation state is getting more negative, then it is going through reduction. We also saw that our oxidizing agent is the thing that gets reduced. Again, it causes the oxidation in something else, which is why it's called that. And our reducing agent, again, is the thing that gets oxidized as it causes the reduction in the other substance that's present. So we talked about balancing those guys, again, using water, H plus and electrons, and OH minuses if it's basic. We then started talking about really redox reactions in sort of the context of galvanic cells. So galvanic cells, we sort of talked about and saw last time, has some major sort of components, if you will. There's one side of the galvanic cell, which in a laboratory, typically you would make using a beaker, some solution. A solid electrode is typically kind of dipped into the solution. So for example, if the solid electrode was zinc, you would have a solution of zinc ions floating around, and it connected through a wire to a voltage meter. On the other side is the cathode side of the galvanic cell. Same deal, usually a beaker there with some solution. For example, if the solid is on the other side, copper, we would have a solution of something like copper 2 floating around in there. Those two beakers are usually connected, and they're connected through a salt bridge. And the salt bridge usually has some type of ionic compound, which is, again, why it's called a salt bridge. That means basically it has positive and negative ions in it. And as we sort of talked about, it helps really stop a kind of big buildup of charge on one side or the other. Again, those ions in the salt bridge will sort of migrate one way or the other, depending on sort of the charge that's getting built up. And again, sort of to keep the charge difference at an appropriate level. Again, otherwise, as we talked about last time, if it sort of just all builds up on one side, eventually the electrons will kind of stop moving from one side to the next. In addition, we also saw that the anode is where oxidation occurs. So on the anode side of the cell, that is where we have that oxidation occurring. And on the cathode side, that is where we have the reduction part of the reaction taking place. So typically our electrons are traveling from the anode side over to the cathode side. And again, the idea here is those electrons, as they're traveling sort of through the wire, if you will, could technically be used to do some type of work or something like that, as we will see and talk a little bit about today. Now, there are something known as the standard reduction potential, or the SRP values. And this is, as we saw, sort of a table of reactions. And since they're standard reduction potential, they're all written as reduction reactions. And basically, they came up with sort of voltages for each of these reduction reactions that happen. And they did that by basically making a hydrogen electrode as a standard. So that was that standard hydrogen electrode, or the She. And it had a voltage of sort of given of 0 volts. So as we sort of talked about, they're able to kind of hook up other electrodes and have these reactions take place and really measure the cell voltage. And they're able to come up with the actual SRP value for a particular reaction. Now, to calculate the E of the cell voltage, the cell potential, the EMF of the cell, we can use an equation. And this was the equation we talked about last time. And as we talked about last time, there's a couple ways to sort of use it. One way you could use it is, as we see on the screen here in the top right there, you could do E of the cell equals E of the cathode minus E of the anode. And as we talked about last time, remember that if you are going to use it in this version, which is sort of the subtracting version, that when you go to that table of SRP values, you should not change the value that you find in the table in terms of the sign. The reason why you technically should change the sign in what you find in that table is because these are redox reactions, which means there should be a reduction reaction, which is what you find in that table, but there also should be an oxidation reaction, which is not what you find in that table. It's actually the reverse of what you see in that table. And as we talked about, when you go that table, the E value is written specifically for how that equation is actually written on the page. And technically speaking, for your anode, which is your oxidation, you technically should reverse it, which means when you reverse it, you do change the value of E for that half reaction. And it goes from, say, positive to negative or negative to positive when you reverse it. So technically speaking, like we talked about in this particular problem, which I think is where we finished up, we figured out that the silver here was our cathode, the magnesium was our anode. So if we just wanted E of the cell, we could go right into this equation, and these would be the values, obviously, that we'd find from the table. And even though that this is the anode one and an oxidation reaction, even though it's written there as a reduction reaction, we would not change the sign. So as we talked about, that is why it is subtract here, because it will always change the sign for the anode for you. So it'll do that switch for you. Now, as we also talked about, I think on this problem and the previous one, was that technically speaking, if you did flip this bottom equation with magnesium around, you get this guy right here, sort of in the middle. And the way that is written, that is an oxidation reaction or an anode reaction where the electrons are coming off on the product side. And the E value for that would not be negative 2.37 like it is for the reduction one, but it would be positive 2.37. So as the question was yesterday, you specifically wrote that equation of magnesium going to magnesium with a +2 charge and 2 electrons. The E value associated with that should really be positive 2.37 volts. What that means is if you do it sort of correctly and flip the sign and flip the value, you actually should add the values together. So if I took that 2.37, negative 2.37, and flipped it and made it positive 2.37, I then should add it to the 0.8 that I had. And as you see, you'll get the same answer. And that's what the two on the top right are. The second one, we actually flip the sign ourselves, and then we add it. So as we talked about last time, probably best to kind of choose a method and stick with it. Again, you don't want to change the sign and then subtract, because you're going to undo what you did and turn it back to the wrong answer. So, important to remember that. We also talked about really the idea of how do you know sort of what is the anode, which one is the cathode. And as we talked about last time, you can use the SRP value to determine that. Again, the idea here is whatever one is more positive is typically the guy that would I'll spit that out, right? Whichever one is more positive is typically the one that would be reduced, which means that would typically be your cathode. So when you go to the SRP table, if you're comparing values like we did here, the silver at 0.8 volts is more positive than the magnesium at minus 2.3 volts. And that means that the silver here should be our cathode. And by default, the other guy would be our anode. Now, remember that there is sort of an asterisk with doing that. And the asterisk is if you are actually given a reaction in a problem, or you're told in words how something is happening, you actually do have to look at the reaction and see what is being oxidized and see what is being reduced. And whatever is being oxidized would be your anode, and whatever is being reduced would be your cathode. So if you're not given any information how the reaction is sort of occurring, you could go with the more positive. But if you are, you do need to kind of see what's happening. Any questions on any of that stuff we talked about last time? Okay, so now that we talked a little bit about E of the cell and the cell potential, we're going to basically kind of tie it together a little bit with one of those thermodynamic values that we've been talking about in a previous chapter, which is free energy, or that Gibbs free energy. And the work that really can be accomplished when the electrons are really transferred through a wire depends on sort of that thermodynamic driving force. So again, there's sort of that driving force that happens that's going to make those electrons want to go from one side to the next. And the EMF, or the cell potential, or the potential difference, is equal to the work divided by the joules. And 1 joule of work is required, are produced from 1 coulomb of charge as they sort of transfer those electrons from one point to the next, via a wire. So ultimately, when we sort of tie it to our delta G, and we talked a little bit about work, or you talked about work before, probably with energy, the maximum amount of work that you could do on something is equal to the delta G, or the free energy. Again, that's sort of the definition of free energy. Again, that energy that's available to do some type of work, either on something or work being done on it through that process. So we could take what we know here about the cell voltage and tie it to our thermodynamics through some relationships. So let's take a look at that. So this brings sort of a relationship, or a couple of relationships that we will see in a second here. Just kind of pop those up there real quick. Okay. So this equation here is the relationship between delta G and E. And delta G, which is our Gibbs free energy, equals minus N, which is the moles of electrons that are being transferred. F is a constant, that's Faraday's constant. So Faraday's constant is 96,500 joules per volt per mole. And remember, a joule over a volt is a coulomb. So that's where that sort of C comes from there. And that's a constant. And this is our E of our cell. So that E of the cell is the same stuff we've been doing, our cathode minus our anode. Again, if you choose, obviously, to do the minus part of it. So what does this mean in terms of the relationship between E and delta G? So we know from our previous chapters that the delta G equals negative. It's a spontaneous reaction. And if delta G equals positive, it's a non-spontaneous reaction. So if we think about the cell voltage and we think about what's going on with, really these numbers here, if my cell voltage is positive, my F is a positive number, N is going to be a positive number. That means no matter what happens, I'm going to end up with a delta G that is going to be negative, and the reaction will be spontaneous. So that's when we say we have positive voltage. That's good. Positive voltage usually means a spontaneous reaction is occurring, because it will give you that negative delta G. And that's opposite if you had your negative E value. If you have a negative E value, negative and negative is going to turn your delta G into a positive value. And that would mean that that reaction is non-spontaneous. That's also why negative voltage, not so good. Right? So negative voltage, non-spontaneous sort of process that occurs. So this delta G equals minus NFE. The important part also is N. N is the total number of electrons that are transferred. So what I mean by that is basically in a redox reaction, you have an oxidation, or in this case, the anode reaction, right? Which is going to lose a certain amount of electrons. So let's just say that the anode reaction loses 4 electrons. The cathode reaction, or the reduction reaction, will gain 4 electrons. So in each of the half reactions, you'll see 4 electrons and 4 electrons. The end value for a reaction like that is just 4, not 8. So you don't add them together or anything like that. So the idea there is whatever number of electrons that were lost by the anode is the exact same number of electrons that was gained by the cathode. So when you calculate N, it really is the balanced number of electrons in one of the half reactions, and that's a good way to sort of remember to get the right number. So you don't want to add the electrons in both half reactions together, again, because they technically are the same electrons. Whatever electrons were lost by one are the same technical electrons that were gained by the other in that sense. Now, so that's an important equation that relates our delta G to our E. We also cannot leave out our equilibrium, right? K value. So this is the relationship between E of the cell and the equilibrium constant. E of the cell equals RT-NF natural log of K. These are all of our same normal sort of things. R is our gas constant, which is our 8.314. T is our temperature in Kelvin. N is our number of moles, just like it was above. F is our Faraday's constant. And K obviously is our equilibrium constant, products over reactants, just like normal. So these two guys here, this one here, it's an important equation you need to know. And this one here as well, obviously you do need to know. Now, if we're at sort of standard conditions, which basically means 25 degrees Celsius, at 25 degrees Celsius, the temperature is going to be 298. It's going to be 8.314 and 96,500. These all become like constants. So at 25 degrees Celsius, that top equation can reduce to these two versions down here. Now, one is, as you can see, the natural log of K, and that is 0.0257 volts over N. And the bottom one is the base 10 of log there, or the log, which is 0.0592 volts over N. You can use either one. They both will get you there. But again, you can only use those two on the bottom if you're at obviously 25 degrees Celsius, which in a lot of cases, that is probably where you're at in terms of the temperature. If you don't want to worry about these two on the bottom here, you don't have to. It is basically this equation right here. So you could just plug in the numbers, even at 25 degrees Celsius, just plug in all the numbers and you'll be fine. I will say that depending on which version of that equation there that you use, if you use sort of the one that's in the box or maybe one of the two bottom ones, you may get a slightly different answer. And usually that difference comes in like the number part. And if there's an exponent, usually the exponent's good, but the number might be slightly off depending on rounding. And that's because, again, you're using like natural log, you're using log in there. So again, just some slight rounding when you use something like natural log or the regular log can make a little bit of difference in terms of the number that you get depending on how you round it. So if you don't want to worry about, like I said, I would just go with this equation here and just remember it and just plug and chug all the numbers in and you'll be fine. So that brings us to our triangle here of our trifecta of wonderfulness. This is our ways to go from all of our sort of values that we've been talking about in these last couple of chapters. We have our delta E, our cell voltage basically. So if we have the cell voltage, we could get our delta G naught. If we have the cell voltage, we could also get our equilibrium constant, again, using these two equations on this page. If we have our delta G, we could get our E. We could also get our K and vice versa. So we could use all three of these sort of formulas to calculate a lot of thermodynamics type of properties. So in terms of sort of relationship in this equation and how it ties into the previous delta G naught one that we saw earlier with the equilibrium constant is, they all really do sort of tie together in terms of values and things that we would expect. If we If we have a negative delta G, that would mean that, again, our negative delta G naught would mean that the products are favored, that probably the reaction is heading towards the product side. That also would mean that we would have a lot more products, and the equilibrium constant should be greater than 1. And as we've been talking about, what will kind of help that reaction go to the product side is having an E value that is positive. So again, all those things really do sort of work together like we've talked about, and does make sense. Same thing as the opposite there. If we have a positive delta G naught, that essentially means that reactants are favored. And basically that means if reactants are favored, we're not going to have more reactants. We'll have more reactants than products, which means our equilibrium constant should be a smaller value. And the E of the cell would be negative in that case, which means it's not going to be spontaneous. It's just going to kind of hang out over on the reactant side. And obviously, if our E of our cell is 0, when you put that in there, you're going to get basically some zeros, and your equilibrium constant will be 1. So kind of equally favored, but probably going to be relatively small in terms of the equilibrium constant. So why don't you take a moment here, calculate the delta G naught for the following reaction and determine, is it spontaneous? So see what you come up with. Okay, let's take a look here and see. So we want to calculate delta G, and we're given pretty much our SRP values. So that should allow you to think about this equation here. So we do want to figure out E of the cell. So we want to figure out our cathode and our anode. And hopefully that you determine from the information given that this should be our cathode. And this here should be our anode. So just like we talked about previously, you do have a couple of options how you're going to do that. I am going to use E of the cell is E of the cathode minus E of the anode, which means I am not going to change the sign from what I would find on the table. That means that if I put it in there, I would have my cathode, which is 0.34 volts, minus my minus 0.44 volts. And that's going to give me 0.78 volts as my E of the cell. Now, again, if you did flip the sign, you would add those numbers. So if you did flip it, you would take 0.34 plus 0.44, and obviously should end up in the same spot. Now, when we look at this, we could actually see from these half reactions, again, since this technically is the one that we would flip, we would have our copper we would technically flip this guy around. And again, this is, as I was just mentioning, if you add those together, since you did flip the sign, you get the same voltage there for E of the cell. And if we do add these together, we can see I got 2 electrons there, 2 electrons there. Everything's good. It's going to cancel. So in this case, N would equal 2 in that particular case because of that. Again, here, N would not equal 4. So we're not going to add these together. But the total number of electrons that are being transferred again is 2 are being lost and 2 are being gained, basically. So N would equal 2 in this case. So that means that we pretty much got everything that we need for here. That's going to be negative 2 moles times our Faraday's constant, which is our 96,500 joules per volt per mole. And then that's going to be times by our E of our cell, which is 0.78 volts. Volts will cancel, moles will cancel. Going to leave us joules here in terms of our units. And that will get us something like minus 150 by 40 joules, or if you want to clean it up a little bit, probably minus 151 excuse me, kilojoules. Any questions on that? Or maybe 150 kilojoules might be better sig fig wise. Now, what does this mean? This means a couple of things as we talked about. I see a positive E, which tells me we're going to have a spontaneous reaction. And you really could stop at that point. But we also have a negative delta G, which all says that this reaction is heading towards our products. Products should be favored, and this reaction would be spontaneous. And if we had to figure out what is going on in terms of K, we would also probably expect a large value of K here since everything's heading to the product side. Yeah, so in terms of the N value, the N is the total number of electrons that a good way to think about it is not the total number of electrons when you add up both half reactions, but it's the total number of electrons that basically have been transferred. So from the anode side to the cathode side. So although in this case, both half reactions have 2 electrons, these technically speaking, if you think about it sort of in a galvanic cell situation where you have your anode and your cathode, just a basic, those 2 electrons are the same. I'll just draw 2 here. Those are the same 2 electrons that started at the anode, ended up at the cathode side. So the total number of electrons are 2 and not 4. Again, because when it gets to the cathode side, those are still the same electrons basically that came over. So the easy way to do it is just, you want to make sure, obviously, like a normal redox reaction, that the electrons are balanced, right, in both half reactions. And once you get them balanced in both half reactions, that's going to be your end value. Again, because the idea there is they're being transferred. So whatever that number is that leaves one in the oxidation step is the same number that comes in on the reduction step. So N would be 2 for the number of moles of electrons. Other questions? Okay, so I think you might have another one here. Why don't you give this a go, see what you come up with. Here we are looking for the question, or trying to answer the question, will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3 solution? So take a couple of minutes here and see what you come up with. See if that will happen. Okay, so let's take a look and see what we came up with here. So again, we want to figure out basically, will nitric acid dissolve gold metal to form gold 3? So we do have some SRP values given. So, probably our E of a cell formula, whichever version you want to use there. It's probably a good idea. So we want to figure out what is the cathode, what is the anode. And in this case, hopefully you figured out. Well, let me start with this. Maybe you went with this being your cathode and this being your anode. And if you did that, you would be wrong. So that is incorrect in this particular case. And it's very common people will come up with that because they go with the gold is more positive, so it should be our cathode. But again, remember that what we were talking about was if you're given information about how this reaction is taking place, you need to sort of think about, what is happening in that reaction. And specifically in this question, it says, will nitric acid, which is HNO3, react with gold metal, which is gold with no charge, to form gold with a +3 charge, blah, 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 the rest of the stuff, right? So that would imply that if we look at these reactions, this is our nitric acid basically here. And that's on the left-hand side, which is actually where we need it. But when we look at the bottom here, that is where the gold is on the right-hand side, which is where we do not need it. So because of the reaction that we're actually doing, we actually need to reverse the bottom reaction, which means when we reverse that bottom reaction, we will actually get the reaction that we're looking for, which is nitric acid plus gold, solid gold, forming AU3+. Also means that technically speaking, when we flop that around, that's going to be minus 1.5 volts, which means if we go into our E of the cell in this case, because this here is actually our anode, and this is our cathode. And if we go in there, we get 0.96. And again, I'm going to subtract because I did not flip the sign here. Minus 1.5 volts. That is going to give us minus 0.54. Huh? That's a bad 4 there. Let's try that again. 54 volts. And really at that point, when we see a negative value here, we actually know that this is not going to happen because negative means pretty much non-spontaneous. To verify that, we could look at the equation or formula we just saw, which is minus NFE. We actually don't necessarily need to put in the actual all the numbers. I'll just do it like this. But when we put in this number here, which is negative, that negative and that negative is definitely going to give us a positive number for delta G. I'm subtracting 1.5 because it is our anode in this case, and I didn't flip the sign. And that would obviously give us a positive delta G. So all of those things together would tell us that this would not occur. And actually, right, that is sort of how they test gold. We used to test gold in pawn shops that way. You put some gold on, some nitric acid on your gold. If it's still there afterward, congratulations, it's gold. If it's gone, not so much real gold. So again, remember that I did not change the sign because of I subtracted. If I went with the one that was changed, I would add those numbers. And that gives me minus 0.54 volts. So again, if you did change it, you would do that. So remember, if you change the sign, add. If you don't change the sign, then subtract. So in my first case there, I didn't change the sign. That's why I subtracted. And again, if you do change the sign, then you can add them together. Question is, yeah, so again, in this particular one, just so we're clear as to why the gold was our anode in this case, and the nitric acid was our cathode in this case. So a lot of people, and I imagine some of you did as well, just went with the more positive one. And the more positive one is technically going to be your cathode. But it will only really be your cathode if you're not told any information about what is happening. But very specifically in this problem, it specifically said, will nitric acid dissolve gold metal, which are these two guys here. And these two guys are basically our reactants, right, which are on the left-hand side of the arrow. And when we look at our half reactions that we started with, our nitric acid is on the left-hand side, but our gold metal with no charge is on the right-hand side. And that implies that when we add these together, in order to get the nitric acid on the left-hand side and the gold metal on the left-hand side, we actually need to flip the bottom equation. And because we have to flip the bottom equation in this case, when we flip it, it no longer is a reduction reaction, right? This is a reduction reaction. When we have to flip it to get this guy on the right side, it now becomes an oxidation reaction, or the anode, if you will. And because we did flip it, technically speaking, the E value that goes with it would be that guy. So again, it's specific in this question because they actually did tell us what is going on and what reaction we're looking at. So again, as we talked about many times, you could go straight off of the positive value for cathode if you're not given any other information. But if you are given a reaction, or like in this case, you're given information in words, you have to go by what it says, right? So you have to see what's being oxidized and what's being reduced. Other questions on that? All right. So the end result is no, this will not happen, right? So the actual answer is no, this will not happen. That's exactly what it means. So because the delta G is positive, and also, honestly, because the E value is negative, they both are pretty much situations where this reaction will not occur spontaneously, and we would not expect nitric acid to dissolve it. Other questions? Okay, so I think you have another one here. Let me see what you need here. Let me give you some values that will be helpful for you to solve this. We want to know what is the equilibrium constant for the following reaction, the SRP values from the table, which don't seem to be here. So let me find it here. The iron 2 is minus 0.44 volts. And the silver is what we just saw in the last one there, 0.8 volts. So that should be what you need there. All right, see what you come up with here. We're actually looking for the equilibrium constant in this one. Okay, let's take a look and see how we're doing. So we're looking for the equilibrium constant. So obviously that is sort of a big hint that you should use something that involves equilibrium constant. And really, we've only seen sort of this equation here. And we do need to figure out a couple of things. Obviously, we can figure out E of the cell since we have the SRP values given to us. R and T, we can figure out, obviously, F is a constant. We also need to figure out what's going on in terms of cathode, anode, and also electrons. So let's take a look. First off, we should figure out, hopefully, that the cathode in this case is going to be the iron, while the anode will be the silver. So again, this is a situation that although the silver is more positive with the SRP value, if we actually look at the equation and see what's going on, the iron is going from +2 to 0, which means it is going to be reduced. It's heading in that direction in terms of that number line. The silver is going from an oxidation state of 0 to +1, which means it is being oxidized in our anode. So again, because we were given the overall equation here, we do need to see what is being oxidized and what is being reduced, and that will give us the proper cathode and anode. Any questions on that? So again, it's good practice not to just go blindly with the positive guy here, especially if you see a reaction given to you. You should actually look and see what's happening in that reaction. Now, the other thing we need to sort of figure out is what's going on with electrons. So this guy is going to gain 2 electrons, right? This guy is going to lose an electron, but they're not really balanced, right? So to balance this, we technically have to multiply our anode by 2. And that would tell us that N in this case is going to equal 2. Again, that is our balanced number of electrons. So basically the silver in this case is giving up 2 electrons. The iron is picking up 2 electrons. So N would equal 2. So now we got N. F is again a constant. Our temperature is 25. So we could add 273 to it to get to 298 Kelvin. And now that we have our proper anode and cathode, again, whichever way that you choose to do that, I am again going to roll with the subtraction, which means I'm not going to change the values that I find on the table. Again, if you did change the value, you should add. So I'm going to get minus 0.44 minus a 0.8 volts, going to give us an E of the cell of minus 1.24 volts. Any questions on that so far? Just so you know, at this point, we should be able to make some predictions about what is going on. I have a negative cell voltage, which is probably going to mean my reaction is going to be non-spontaneous, right? Because that's going to lead to a positive G, which means both of those things should mean that reactants are favored. And my equilibrium constant should probably end up being a small value. So again, all these things should sort of tie together as you're going through the calculation. So now we could actually get to our calculation here. This is also the one where we saw sort of a reduced down version of it, where you could use something like 0.0257 volts over N natural log of K, or you could use the other one with the 5 in it if you want, and the log of K. I'm just going to plug it into here. And that means that our E of the cell is minus 1.24 volts. R is 8.314. Temperature going to be 298 divided by our N, which is 2, and our Faraday's constant, 96,500 joules per volt per mole. And the natural log of K. We got some K's canceling, some moles canceling, all that good stuff. So I'm going to clean up everything here. And if I clean up everything, I'm going to basically take 8.314 times 298, hit the right number, 8.314 times a 298 divided by 2 divided by 96,500. I am then going to take minus 1.24 and divide that by that number. That number was, by the way, 0.012837. And if I do something here, minus 96.59 equals the natural log of K. So again, I cleaned up everything on the right-hand side. I divided it to the left-hand side. And now to get rid of the natural log, we want to take E of both sides, right? And if I do that, that's going to give me a K value of, we'll call it 1.12 times 10 to the minus 42. Any questions on that calculation there? Now, again, if you happen to have chosen, you know, one of those other versions of that equation, like we saw on that page, like the 0.0257 volts over N, natural log of K equals E of the cell. Again, like I said, depending on the rounding, you may get a slightly different answer on the front part here. But this part of the numbers should be dead on usually. So again, depending on which one you choose, you may see a little variation, but you should get something like that. That obviously I would classify as a small K value, which does match up with everything in this problem. Again, our negative E, which should give us a positive G, and a small K. So again, all those things do make sense. Any questions on any of that there? So again, this is another very good example of you want to make sure that you look at the equation if you're given to it. Yeah, so for example, it just has to do with rounding as well. So in my experience, that's what I got when I did it with the 0.0257. So somebody got 1.28 times 10 to the minus 42. And like I said, a lot of that really is kind of the rounding aspect of it. And because in some cases you're using the regular log, some cases you're using the natural log. And again, if you just round a little bit on that, you'll get a slightly difference in that front number. Again, the back number should be pretty on there, the exponent part. So it should be okay. And probably if I, let me see here. If I rounded mine to 96.5, I would get 1.23 times 10 to the minus 42. And again, that's pretty close. The truthful answer is I didn't really round on my calculator. So when I took the E, I took the E of minus 96.59456 and so forth. And I didn't really do much rounding. I just kind of continued on my calculator. And that's what got me to that number. But if you did round to minus 96.5, you would come to something like 1.23 times 10 to the minus 42, which would be closer. So it's a lot of it has to do with the rounding aspect of it. And sometimes people are used to not rounding till the end. And if you just kind of continue in your calculator, you'll get some variations in that front number and stuff like that. But everything would be okay in terms of the answer on that one, I think. Other questions on that? Okay. So let's see here. Yeah, so that rounding part, and especially when you start to deal with the logs and the natural logs and the inverse of those things, it does make a kind of a big difference sometimes depending on how you round. But usually that exponent number, like I said, usually will be okay. All right, so let's talk about what happens now when we sort of get to differences in concentration and how it sort of affects the the E of the cell. And this is going to tie together some equations that we saw earlier in some previous chapters. That's some of our thermodynamic equations and also our delta G equations. Again, remember that technically speaking, this delta G has to do with spontaneity, whether it's going to be spontaneous or not, while delta G naught has more to do with sort of equilibrium and whether or not, reactants or products are favored. You could kind of almost think they're kind of the same thing. Again, if products are favored, then probably the reaction spontaneous heading to products and vice versa. So kind of combining these two equations plus the thermodynamic one we saw earlier where we were talking about under sort of non-standard conditions with our Q, we get an important equation, and this is what is known as the Nernst equation. And again, the Nernst equation here is one that you should know. And let's talk about sort of the differences here and these kind of things that we see. And basically, it's kind of the same situation as what we got going on up here. And that E, that first E is, you could kind of think about it as sort of E of the cell under non-standard conditions. This would be our E of the cell under standard conditions, like the SRP table. You do your cathode minus your anode using your SRP values. The R and the T is the exact same thing we've been using in that last problem there. That's the gas constant, the 8.314, the temperature in Kelvin, and it's still the number of moles of electrons. F is our Faraday's constant, and Q is our good friend that we've seen all semester here. That, again, is our products over our reactants. Just like normal, our coefficients become our exponents and everything like this. So we use the Nernst equation kind of similar to how we use this equation here, which is there's something that is not under standard conditions. So remember that when we talk about sort of standard conditions, we're talking about pressures that are 1 atmosphere. We're talking about molarity that's 1 molar. We're talking about temperature that's 298 or 25 degrees Celsius. So again, if something is not under those sort of standard conditions, we would want to use the Nernst equation and see what happens in terms of, will the reaction become spontaneous, not become spontaneous? So, there is technically a way you could kind of play with things like pressures or concentrations and potentially turn a reaction that normally is not spontaneous into maybe a spontaneous reaction, or vice versa, right? You could kind of turn a spontaneous reaction into a non-spontaneous reaction by playing with things like concentration, pressures, those type of things. Just like we saw in the previous one, at 298, which is 25 degrees Celsius, you could reduce these equations down the exact same way. And by the way, this equation that we see here in the box is actually how we get to the original equation that we used just a second ago. So if you remember a second ago, we had E of the cell is equal to RT NF natural log of K. And that's the equation that we just used. And that is because when we get to equilibrium, Q becomes K and E would equal 0, which means if you substitute those guys into that equation, that is essentially where that equation that we just used actually came from. So that one that we used previously actually does sort of come from the Nernst equation here. Again, we use the Nernst equation in a situation where we may not be at equilibrium. Something is not at standard conditions. You want to calculate that way. Same kind of thing as I said before. You could ignore the 2 bottom equations and just plug and chug into the top equation there that's in a box. And you should get, again, pretty close to the same answer no matter which one you do. Just like we just saw, though, maybe slightly different with some rounding. So why don't you give one a go here and see what you come up with. Again, let me give you the SRP values. So the SRP for iron 2, same as what we just had, I think, minus 0.44 volts. And for cadmium, it is minus 0.4 volts. All right, so will the following reaction occur spontaneously at 25 degrees Celsius if the iron 2 is 0.6 and the cadmium 2 is 0.01? So take a couple minutes to see what you come up with. Okay, so let's take a look here since we're getting kind of to the end. So we want to know, will this reaction occur spontaneously? A couple of big sort of hints as to maybe where you should go in terms of how to calculate it is like right here. We're given some concentrations, and those concentrations are definitely not 1 molar, which would imply that this reaction is probably not under standard conditions. And we're looking for like E of the cell since we have some SRP values given to us. So that should point you in the direction there of the Nernst equation, which again, if you use the one that's not reduced down, looks something like this. So we do need to figure out a couple of things. We do need to figure out E of the cell, which is again our cathode minus our anode. And in this particular case, our cathode is again going to be, hopefully we got the right one here, it is going to be the iron 2 again in this case. Because when we look at the overall reaction, it's going from +2 to 0, which means it has gained some electrons. Yeah, 2 electrons, by the way. And that means by default, our anode should be the cadmium, going to cadmium with a +2 charge, which means that it lost 2 electrons in this particular case. That is also different than what we would get if we went by the values that were given to us. Again, if we went by the more positive one here, the cadmium would be our cathode and the iron would be our anode. But again, because of that overall reaction, we do actually have to look at it and see what's happening. So this also helps us with one thing that we need, N is going to equal 2 in this case, right? As 2 is the number of electrons being transferred. And now that we got our cathode and our anode, our E of our cell should be our cathode, which was the iron. So that's going to be minus 0.44 volts. Again, I'm going to subtract, so I'm not going to change any signs. And that means that my cadmium would be minus 0.4 volts. And that's going to give me E of the cell of 0.04 volts, negative 0.04 volts. First off, any questions on up to this point? We're not obviously done with it yet. But it does tell us something here. It tells us that under standard conditions, if everything was 1 molar, 25 degrees, you know, all that good stuff, this reaction here would have a negative cell voltage, which means that this reaction would be positive G and be non-spontaneous. So under standard conditions here, this reaction should be non-spontaneous because of that. So what we're looking at is we're not under standard conditions. So we want to see is maybe this will make it spontaneous or maybe it won't. So let's take a look at that. We now have pretty much everything we need to go into our equation. Just so we know from the overall equation, our Q is going to equal the concentration of cadmium with a +2 charge divided by iron with a +2 charge. This guy and this guy are solids, which won't be included, which is also why you have no numbers for them. So that means that E will equal our E naught, which is minus 0.04 volts, minus our R, which is 8.314, minus our times our temperature, which is 298 in this case, divided by N, which we figured was 2 moles, and our constant 96,500, or Faraday's constant, natural log of Q, which is going to be cadmium's concentration, which was 0.01, divided by iron's concentration, which is 0.60. So if we do some cleaning up, we get minus 0.04 volts minus, and if we do everything on the right-hand side there, we end up with minus 0.0526. I'll round a little bit. And altogether, that ends up giving us an E of the cell under these conditions of 0.013 volts. So under these conditions, these sort of non-standard conditions, the E of the cell is 0.013 volts, which is now a positive E, which technically should give us a negative G, and technically should mean that this is going to be a spontaneous process. So this illustrates that you could have a normally non-spontaneous process like we do here, that under normal standard conditions would not occur. But by playing with the concentrations that are in here, we were able to kind of turn this guy into standard conditions. Yeah, 25 degrees Celsius is a standard condition, but remember, sort of when we talk about standard conditions, it kind of has to have it for everybody, I guess, is the way to kind of think about it. So in this case, we had concentrations and temperature. So although the temperature was 25 degrees Celsius, which is standard conditions, the concentrations were not 1 molar. So that part of it was the kind of non-standard conditions that we were dealing with in this sort of reaction. Other questions I can answer for you on this? So again, with the Nernst equation, if you use one of those rounded versions, again, maybe slightly different depending on how you rounded, but you really should come up with the same answer. Any questions on any of that there? All right, we will lay it up here for lecture for now. We're going to go to lab, and it's what we've got there, some group 3, I think we're on to. So same sort of deal. You'll get to see the known video. You'll actually get to see it this time with the actual pictures and everything. It'll be good. And then you'll have your kind of individual unknowns like last time and stuff like that. So I'm going to say we're going to start lab at 3:10. I just need a couple more minutes to kind of set a couple of things up for it. So why don't we start lab at 3:10, take a little extended stretch, and we'll come back and do that at 3:10, okay? All right, I'll see everybody at 3:10, and make sure you hit here if you didn't do so, and I'll see everybody in a bit. Sarah, if you're still here, the answer is yes, you can, because the Nernst equation has the Q in it. So you can use one of those kind of simplified versions as well. I think you're still here.